Well, it's time. Welcome back, everyone, and welcome into week number 14. We're definitely running out of weeks. We're going to have an ordinary week on this one, but next week is going to be primarily devoted to just reviewing for the course. On Wednesday of next week, because our course has a take-home final exam, which is essentially kind of like a glorified final project, but not exactly a final project. It's going to be released at the end of our review. Oh, I said Thursday. I keep forgetting our class is a Monday, Wednesday class. I used to teach this almost exclusively on Tuesday, Thursday. I think that's what's throwing me off. The exam is going to be released after we finish reviewing the course on Wednesday of next week. Let me fix that there. So we'll be releasing the final exam as a take-home exam on the 29th. The due date on that exam, probably best to do it as soon as possible. You have the opportunity to get that off your list before you go into finals week. But I'm going to make the due date be on a Thursday, May 7th. Maybe that's why I'm getting mixed up on Thursday. My due date is just a 1 day back from our typical meeting day. So that's the plan for the course so far. And again, congratulations, we're nearly there. We got through our third exam. Check in the Canvas for your exam score, your current course score, and the feedback on your exam work. And as far as what else we have going on, we have assignment number 11 due on Wednesday of this week. And assignment number 12, that's going to be our final assignment for the entire semester. We're going to drop after the end of final grades, the lowest two assignments. So that'll be 2 out of 12 it's turning out. Well, any last questions or comments at all, folks, before we start today's work? Okay, well, let's get going. So we're, again, nearly done with the content. I have two more statistical methods that I want to introduce to the course before we finally end. Chapter 22 is going to be an overall test, chi-squared, for two categorical variables. And chapter 24, this will be our final chapter of the entire course. We're going to look into matching a categorical variable with more than two outcomes, along with a quantitative variable. In that setting, we're going to be looking at the so-called one-way ANOVA procedure. And statistical methods, they just keep going and going. If you know you need to take more statistics, a good follow-up course to this one could be experimental design. You look into two-way ANOVA and beyond. Regression analysis would be great to look into other kinds of topics. Modeling with linear regression, multilinear regression, and so on would be great topics for additional courses. But these will be the last ones we'll be looking into this particular course. And so here's how our table looks like at the moment. I need to add one more row here for the ANOVA chapter. But what we did last chapter, the chi-square test, the review there is we had one categorical variable. So we're in this box. For that variable, there are more than two outcomes. So we don't have a notion of successes nor failures. And that's why we use the chi-square test for goodness of fit in chapter 21. The good news about chapter 22 is we're still using the chi-square test, but we're now making an adjustment. The question now we're asking is, what if there are two categorical variables? And I forgot to fix the wording here. What I was trying to convey is two categorical variables, more than one with two outcomes. So it could be one categorical variable has exactly two outcomes, but then the next categorical variable is going to have three or more to fit in this procedure. The reason for that statement there is if it's exactly two categorical variables, both with two outcomes, that's this procedure. We just call them successes and failures, and we could do that analysis from chapter 20 on proportions. But here we're saying one of the variables in this section has more than two outcomes. It becomes chi-squared for two-way tables, our current chapter. So that's the landscape so far. Again, I need to add one more row to fully describe what's going on with ANOVA. But essentially, all we're doing is we're saying we're going over to the chapter 18, and we're saying our categorical variable has more than two outcomes. That's all that does to make it ANOVA. Well, any questions or thoughts at all, folks, before we jump into the chapter 22? Okay, well, chapter 22 starts off by just laying out the whole procedure. I need to borrow results from probability theory, and if you're curious about this, don't hesitate to ask. I can put up a write-up about how these expected counts go, assuming independence in probability theory. But let's go through this carefully because this particular test, I think we talked about it a little bit, is quite a bit different than any other hypothesis test we've done. And chapter 21 was pretty unusual in its own way. Here's the new setting. We're measuring two categorical variables. At least one of those variables has at least three outcomes. That puts us squarely into this particular chapter. And take a look at these hypotheses. The null hypothesis is that there is no relationship between the two variables. The alternative hypothesis is that there is some relationship between the two variables. It doesn't tell you what the relationship is, and that was the same issue we had in chapter 21. If we reject the null hypothesis, our test doesn't tell us specifically why. We have to do a follow-up analysis to know why we've accepted the alternative. And same kind of issue here. But we have some hints on how to resolve this. We'll look into the chi-squared components. Looking at this a little bit closer though, and thinking in terms of variables with a statistical and probabilistic mindset, if you say that there's no relationship between two variables, and you think probabilistically, what you're really saying is the two variables are independent. So our null hypothesis is that full-on true independence between our variables. One variable just does not influence the other in any way, shape, or form. The alternative hypothesis is now saying dependence of the variables. Variables are dependent, but it won't answer the question of why are they dependent? What is the nature of their dependence relationship amongst one another? Again, that would take another follow-up analysis. And that's where other statistics courses could go. Categorical data is kind of its own thing. And there's a lot of follow-up analysis once you go beyond rejecting a null hypothesis to investigate the nature of the dependence relation. So again, these are weird hypotheses. They're not in terms of parameters whatsoever, like every other hypothesis we've looked at. This time, they're in terms of the variables themselves. Any questions so far, folks, with the introduction to the null and alternative? Okay, well, if we have two categorical variables, we can build a two-way table. In chapter 21, we had one categorical variable and we built an ordinary table. What we mean by a two-way table, let's take a peek at one, is if we have variable going this way and a variable going this way, we now build out an entire two-way table to put in all the counts. So these are all the counts for this particular problem, and that's just what we mean by a two-way table. In that two-way table, to address our null hypothesis to come up with a test statistic, we have to come up with the expected counts. And again, probability theory and statistics are completely inseparable. Here we're going to cite a rule from probability theory that tells us if the null hypothesis is true, which means you're using the assumption of independence between variables, the expected count in every single cell becomes this formula, the row total times the column total divided by the table total. It's kind of a strange formula, so again, if you're curious, let me know about that. And I'm happy to do an additional document as a write-up to show how you loop in independence from probability theory with an example like this one to explain those expected counts. As far as we go in this section, our studio is going to crank these out. I felt it was a good idea to explain where they come from, and this is the short explanation here. Aside from that, if you look at the rest of the procedure, everything else is essentially exactly the same, almost. Let's highlight the differences. Our null hypothesis and alternative are certainly very different in terms of the variables themselves. But as far as the chi-square test goes, to test the null hypothesis of no relationship, we have to first check that our data came from two different kinds of sources. This time there's two versions, and we'll look at each version for the examples below. One situation we might have is we have two simple random samples, one from each population, and one of our categorical variables, I said the first one here, but it just has to be at least one of the variables, is just saying what population each individual in their data came from. So that's a context for using chi-squared. Another chi-squared is, it could just be one single sample, and all of the individuals in that sample are classified according to those two different categorical variables. So it's kind of an unusual procedure again for that reason. There could be two simple independent samples, or it could be just one overall sample. Next, excuse me, I'm losing my voice here. I can tell it's the end of the semester almost. No more than 20% of the expected counts are allowed to be less than 5. That's the same exact carryover condition that we saw in the last chapter. All expected counts have to be greater than 1. So that's again another directly carried over condition. The formula for the chi-squared components are exactly the same. And the p-value is almost exactly the same, but here's one key difference. The degrees of freedom that goes here is found in this way. If R is the number of rows in our two-way table, C is the number of columns in our two-way table, the degrees of freedom is the product of the number of rows minus 1 times the number of columns minus 1, goes into that spot. And aside from that, the syntax for the p-value is completely identical as well. So the big takeaways are, if you now have two categorical variables, it could have came from these two different situations. Both of them are allowed. Our hypotheses will look different. Expected counts formula is different. But everything else is pretty much identical. Well, that's our short tour through this formula page. We're going to cite it as we work through the next couple problems. But any questions or comments at the moment? Okay, I want to pull down the conditions as we carefully check them in the next problem. Let me just park it down here for easy reference. And here's the context of our courage problem to take a look into. We're told in example 1, a botanist is studying the local ecology of showy milkweed. So an interesting plant. I think we've discussed this plant once before in a different problem. They want to know if the primary pollinator for these plants differs based off the geographical region. So they have two distinct populations we're going to be looking into for these data: milkweed growing in the Snake River Plain and milkweed growing in the Boise foothills. They're both big geographical regions, but if they do their statistics just right, they can come up with great random samples. This is going to be a lot of field work for the botanists. So let's assume they did all of that field work, and this is what the next part of the problem says. The botanist selects a simple random sample of 120 milkweed patches from the Snake River Plain. So that's one sample. Let's throw in a sample size. N1 is 120. And separately, they select a simple random sample of 140 milkweed plants in the Boise foothills area. That's a second sample, so N2 is 140. So now we have really two different populations: the milkweed in the Snake River Plain, the milkweed in the Boise foothills. They took some rather large samples, and after they did all that, they had to observe these plants and see what was pollinating them. For each patch, they observed and categorized the most frequent type of pollinator into one of three outcomes: the monarch butterflies, native bees, or moths. So that fills out our table. We have the region, Snake River, Boise. We have the major pollinators, monarchs, native bees, and moths. And the question says, once you see this table, is there significant statistical evidence of a relationship between the regions and pollinators. There's no way I could tell just staring at the data. And what's trickier is the sample sizes aren't balanced. So to have a better look at this, you probably want to have a relative frequency table, not a counts, because again, unequal sample sizes are skewing the numbers ever so slightly. So are the number of monarchs, bees, and moths pollinating milkweed independent of their region or dependent? That's a great statistical question. It's hard to just stare at the data and come up with an answer. And so that's why we're going to run through the entire chi-squared procedure. We'll use a 1% level of significance, so alpha is set to 0.01. With that, that's our context. I think we're ready to begin. Any questions or comments at the moment? Okay, again, our hypotheses, there are as unusual as we've ever seen pretty much. We're not defining the parameters this time. In place of what we would have put in for parameters, we're instead describing the variables using the context. So to make sense of this, there has to be two variables, but I'm presenting you with a table that's a two-way table of the data, and that's a pretty big hint. This would be variable one. Going this way, going this direction, this would be variable two. The instructions say describe the variables. But if you go all the way back to week one of the course, that's exactly what we were doing, just describing variables, whether they were categorical, quantitative, or some data sets that had a mixture of both kinds of variables. So we're just going back to that skill. For variable one, it already has a good name. Let's call it just region. So one variable is region. It is categorical. We also described the outcomes whenever we were describing a variable way back in chapter one. So let's do the same just for the sake of parallelism. It's categorical with outcomes. Snake River Plain. And Boise Foothills. So that's one variable down. This is plural by intention. The other variable we have to describe, oh, hang on. There we go. The other variable we have to describe is here. It didn't have a header to say what a good name is, so come up with any name that just makes sense for the context of the problem. These are pollinators of milkweed. I'll just call it milkweed instead of showy milkweed. So pollinators is probably just a fine name. Let's call it pollinators. Is the other variable. It is categorical with outcomes. Monarchs. Native bees. Moths. Well, we did it, folks. That's describing the variables. Again, it's kind of unusual because this is so far in example one, exactly the kind of stuff we were doing in way back chapter one. Any questions at all with our description of the categorical variables? Okay, well, let's think about next week for just a moment, because again, the course is almost over, the final exam is looming. When you see these kind of problems come back on the final exam, even if it was exactly this question, it's trickier. And the reason is my problems are going to be randomized. The skill that we're going to be practicing on our review is primarily now picking out the statistical method. So now that we're looking at this, here's our major tool of picking out the right statistical method. And the feature about this one was when we analyzed the variables, one of them had two outcomes. these two regions, and that was it. But the other one had three outcomes altogether. And so we have at least one variable with more than two outcomes. I'm going to try to clean up that language there to make it easier to read. Once we spot that that's the condition for these data, it tells us we're in chapter 22. So again, these problems are easier because we already knew we were in chapter 22. We know the context of the procedure, but we'll be doing some good work when we review on how to determine what is the method in the first place. And it's really this, describing the variables tells us the method. Well, it was also part of the procedure for this particular problem, so that's why we started off this way. Next thing we move on to is stating the null and alternative. But again, these are strange hypotheses. Let's write them out. Test H naught. You can say that there is no relationship between region and pollinators. You don't have to say no relationship between Snake River Plain, Boise foothills, and the pollinators, monarchs, native bees, moths. I mean, you could, but you're writing out a lot of work. Our hypothesis has this form. No relationship between the two variables. We just say what those two variables are. Actually, let's screenshot this down to really emphasize that comment. So when we go to write out the null hypothesis, all we're really doing is going to our variable names, which are here, region and pollinators. Those are the names we gave it. And we'll say there is no relationship between region and pollinators. So that's our null. We're saying independence. That'd be fine to say that as well if you prefer. You could say the region and pollinators are independent variables. Completely fine way to write down your null hypothesis. So we're testing that null against an alternative, not a specific one. This is an overall test. We're looking for any reason that there is a relationship. Again, similar to what we were doing in the chi-squared procedure, when we were saying maybe one equation is false from the null hypothesis, or two equations, or all of them, and so on. Here we're saying essentially not independent. The variables are dependent, but saying there's some relationship is just a different way of saying dependent variables. So we'll say there is some relationship between region and pollinators. Our procedure is not going to tell us what the specific relationship is, but we'll take a little bit to look at chi-squared components to give some idea of how follow-up procedures might go for those that are curious. You can get pretty involved with this, confidence intervals on actual parameters. There'd be 6 parameters to match every one of these cell counts, for an example, and you can give a confidence interval for them. Once you determine you've rejected the null, to investigate further, what is the actual relationship in the first place? But here, it's kind of frustrating. This is just an overall test, be the same kind of idea with ANOVA that we're looking into. So we're testing those at alpha is 0.01. So that's our null and alternative. These will be the weirdest set of hypotheses in the entire semester. ANOVA is going to look a little bit more natural. Well, any questions whatsoever, folks, through parts A, B? Okay, now we have to determine how well does our data match up the conditions in the first place. First thing we're going to determine is just because you have 2 categorical variables is not an actual full-on guarantee chi-squared procedure is going to work. So we're looking even closer. Let's look at what the data told us, or the context. We have a simple random sample of 120 from the Snake River Plain. Another simple random sample of 140 milkweed plants from the Boise foothills. So it's nice that we have random samples. And that puts us in the category of part A. We have simple random samples from two or more populations, exactly two. They correspond to the regions. And the first categorical variable or the second one, it doesn't have to be specifically the first, one or the other. All it does is classify the individuals according to which population they belong to. And that's what region is doing. It's taking all of our data and saying, did it come from the Snake River Plain, one population, or the Boise foothills, another independent population? So we can say on part one, we have simple random samples from two populations. It says two or more, so we're okay there. We're right on the borderline. From two populations. And second requirement is that region, one of our variables, has to tell us where each one of those populations or each one of the individuals in the sample belong to. So we'll say, and region says, or let's say classifies, where each observation comes from. From when we say where it comes from, we mean Snake River Plain, Boise foothills. And again, those are the two populations. So these particular data satisfy part A here. Next example is going to be part B, but it's kind of interesting. There's two different ways to satisfy this kind of chi-square procedure. So beyond that, we need to look into the expected counts. We can't have more than 20% of our cells expected counts being less than 5, and every expected count has to be 1 or higher. If that doesn't happen, our sample size was just too small for these kinds of data. So that's going to be our next stop. Here, we're going to now use RStudio. We did do the expected counts to show how they go for the chi-squared in the last chapter. But once it becomes a two-way table, even for a 2x3 table, that's some pretty tedious work to come up with all the expected counts. That feels like busy work. If you wanted to do it by hand, I think Excel would be a good environment to do it in. So if you like to do it in Excel, not a bad option. But we can make RStudio do essentially everything for us. It can do the expected counts, the test statistic, and the p-value. So we're going to analyze it like we did in the last problem in chapter 21. Make RStudio do the heavy lifting for us. So here's how it goes. The major trick or the new thing that we have to do in RStudio is import the data which came in as a two-way table. Actually, it's not too bad to do. It's just something we haven't done before. Let's go careful with this first setup on the syntax, and I'll make sure to share this in the notes. First thing I want to write down is, let's call this counts. That mirrors exactly what we did in the last chapter. But if it's a two-way table, the structure we're going to use this time inside of RStudio is a matrix. So write matrix, open a parenthesis, and then do a lowercase c to combine the information you see here. The way I want to import the table is the exact way I see it here. So I'm going to type in C, new set of parentheses, and I'm going to go row-wise. 6, 70, 44, comma, separate your values. And you could keep on going, 9, 110, 21. But what I would encourage you to do in RStudio is hit enter and put the data below. That way you can visually see if your data is correctly put in the exact way it should. So 9, 110, 21. Let me put an extra white space here just to line up the commas. And again, that can be just one line, but it's a good idea to hit enter here so we can double check and visually see all the counts are completely identical. Now, here's the next part that is actually kind of tricky. So if you're having any trouble with your syntax on the homework assignment for chapter 22, or maybe you're doing the final exam and the syntax is not working out for this problem, I can't tell you exactly what information is going on here, but if you send me a picture of your screen syntax or copy and paste it, send it into the email, I can help you fix the syntax. Absolutely, just like for other homework problems. So the thing that's really tricky here is RStudio doesn't know how many rows you have, so you must write in n row for number of rows. If you go plural, it doesn't work. It has to be just specifically n rows. RStudio says here in the yellow, desired number of rows. So that looks like we have the right thing. 2 rows in our two-way table. And one other thing. RStudio sometimes likes to import data thinking that you gave it columns rather than giving it rows. So we have to be specific and say by row equals true. So importing it all in exactly that way allows everything to work. Now, everything, the test statistic, the p-value, the expected counts, or we're going to check on conditions, are really fast to find. That's the tedious step right there. So let's see if it ran. Hit down in the console, counts. Hit enter. And yeah, that's our table. It looks weird, right? It's got where the red dot is, comma 2. The reason it has all these commas everywhere is that's how you index inside of the table. If you write out counts, put in a bracket and say you want to get your 70. 70 is in row 1, comma, column 2. So that 2 there is saying you're taking information out of column 2. The 1 here is saying it's from row 1, so it should give us a 70, as we see. If you go 2, 2, it gives us the 110 instead. Well, we've got our table in. And this part, I think it's something you could skip in all honesty. But if you're building out a table like this, it still looks weird without the actual categorical variable outcomes. We can make it look almost exactly like this. So I want to add the row names for the next step. Let's write in row names. Should do the job. It's going to be the row names for the table counts that we're building. That will get combine. Use quotations because this will be a string data type. Snake, river, plain. And the quotes and put in Boise, foothills. Let me actually go down a line so we can see it all on one screen. Boise, foothills. So running that syntax is going to add their road names. We put in the console counts again. We see that this is a little bit nicer to look into instead of just like say 2 comma, like we have up here, comma 2, comma 3, and so on. We have the actual data's categorical variable outcomes. We could do the same thing with the second variable. This one goes call for column names. So call names, counts, get C, and just start listing them in. Monarchs, native bees, moths. So run that, hit Control-A, Control-Enter inside the script. Always want to test this out. So in the console, hit counts again, see what comes out. And yeah, that's basically our table. The only thing I don't have is that column header there that says region, but this will do the job. So our data has been imported. We just basically have to type it in. And again, if you're running into any syntax trouble, you can copy this and just paste it directly into an email. You can take a picture, screenshot, anything like that. Send me a message in Canvas or an email, and I'll get right back to you, helping you make sure that syntax works, whether you're doing a homework problem or even an exam question. So now let's remind ourselves what we were doing. We're checking that the expected counts are large enough. All of them have to be greater than 1, and no more than 20% of the 6 cells can be below 5. So we just need to run the whole chi-square procedure. We're going to borrow the same technique we did in the last chapter and store an intermediary result. Call result gets the output of chi-squared.test, so that operation. Throw in counts. And chi-squared.test really stores a lot of stuff. That's why we're saving it into a variable, so we don't have to run the test a whole bunch of times. It also makes it easy to extract out all the output in chi-squared.test by using a $sign. It's going to give us a whole window of all the information contained there. But if I hit $sign now, it doesn't tell me what's in that method because it hasn't ran. So this becomes a common thing. We did it in the last chapter. We're doing it now, and we'll use it for ANOVA when we're using that method in the next chapter. So run the whole thing. Nothing appeared to happen, but now we're back to condition checking. We want the expected counts. So I'm going to use hash here to comment expected counts is the whole point of this next line. Cite result again, but now if you hit the $sign, here's that menu of good stuff. All we want is expected. If you go to observe, that's just the original data table in the problem. Expected is the counts that this study should have gotten if the null hypothesis is true, no relationship between region and pollinator. So let's see what that comes out as. Let's hit Control A, Control Enter, and here are all of our expected counts. There's a couple ways you could cite these. You could copy and paste directly in. If it breaks the table a little bit, you can kind of fix that and space things out. Another approach is just to directly type them, but that is tedious for 6 expected counts. So an equally valid way is just to screenshot your output so that the table keeps its more nicer format, and that would do the job. I'll leave it up to you. You can copy paste out of the console, screenshot like we just did, handwrite it, whatever feels more natural. So here are our expected counts. Let's give this a title. Now let's review again what the null hypothesis is saying. The first step of any hypothesis test at all is to assume the null hypothesis is true. When we assume that this is true, we're saying full-on independence between the region and the pollinator. And if that is actually true, here are the counts we would actually get. Let's check them out. As far as monarchs go, that is really close. This was 6, this is about 7, this is 9, this is about 8. It's weird to see a decimal when you can't really have 8 and 7/100ths of a monarch, really. But what this is saying is run the experiment over and over and over again, and that's the average counts you should get when the null hypothesis is actually true. In column 2, it's a little bit more different, but not by a ton. Native bees from 70s climbed to 83 expected. Boise foothills at 110 has dropped to 96. So not too different on that end. And then, as far as moths go, this was at 44, dropping to 30. Well, the absolute change is not what's important, it's the percent change. That's a pretty big drop in terms of going from 44 moths to 30, and going from 21 moths to 35, that's a pretty big drop as well. So let's see what happens now if we get the test statistic and the p-value out to see if these expected counts are different enough from the real counts in order for us to reject the null hypothesis. Well, any questions at all, folks, with expected counts? Okay, again, this is where RStudio shines a lot because you can imagine this can be a 6x10 table. That's completely appropriate. That might make the most sense for the right context. And computing out in a 6x10 table all the expected counts is 60 computations by hand. That just becomes way too much work. That's like calculating a standard deviation by hand in a sample size 50 or something along those lines. So now our next operation is the test statistic. Well, we've already got it. It's inside result. We just have to pull it out. So here's our next level of the syntax. Let's go and just call this test statistic and p-value. Cite result again, hit the $sign, our menu board of things it's got. And this time we want none of those. You know, I forget, for this particular step right here, just citing results does the job. If you hit result, it's going to output the table we expect. So leave it just like that. Hit Control A, Control Enter, and there it goes. If you just put in result, it outputs Pearson chi-squared test. And a nice formatted table here. Chi-squared is 16. Degrees of freedom is 2, but that's because it's the number of columns minus 1 times, so 1 times, the number of rows minus 1, just a 1 times 2 for degrees of freedom, resulting in 2 itself. And the p-value is tiny. This looks like significant data. So let's put down here, test statistics, 16.185. Chi-squared is the way we typically denote it. So that part was done. P-value. Let's cite that as well. The p-value for this is 0.0003059. There's 4 significant digits on that one. At any reasonable alpha, ours is at 0.01 for 1%. We are certainly rejecting the null hypothesis. So I'll put here, just as a comment in orange, this is less than 0.01 equals alpha, which implies reject H naught. We now have statistical significant evidence in favor of the alternative. There is some relationship going on between region and those top 3 pollinators. So kind of fast analysis. Once we get the data pulled in, that's the tricky step for sure. Everything else flows pretty fast. And we're just using our knowledge about statistics, how things go, to get through the last part, writing down the conclusion. Any questions, comments, or thoughts at the moment? Okay, well, let's pull down our hypotheses. Normally, we would cite the parameters as well, but this time we're citing just the variables themselves. Aside from that, we're not doing anything too different from what we've done on every single hypothesis test. If we find a tiny p-value, and this one is quite small, then we have evidence that the alternative is true. We want to write this out in terms of the context. The full context is not here. We need to go beyond that and say what regions, what pollinators. So that's where we're using our full-on definition of both of the variables at the same exact time. So a full conclusion using the context expands what the variables are in the very first place. So it could go something like this. We have significant statistical evidence this time at the 1% significance level that now we talk about the variables. There is something going on between these 2 variables. We don't know the relationship of them, but we know that they are related. There is some relationship between region and pollinators, but again, we need to pull in the context and say what regions between Snake River Plain and Boise, foothills, and the pollinators, monarchs, native bees, moths of, remember this was all about pollinators of milkweed. So we'll say here, of milkweed. And maybe to make this flow a little bit better, instead of using this and, because I have another and here, let me pull that one out. I think it's a better design choice to just put a comma. We have some relationship between Snake River Plain, Boise foothills, and this says switch to the other variable, pollinators, monarch, native bees, moths, of that milkweed plant. I think they called it the showy milkweed, but we'll call it just milkweed here. So there's some relationship. Who's pollinating what depends on the region, by what numbers. Well, we did, folks. That's our complete rundown. But again, it leaves a lot to be desired here. It's kind of weird to end a problem like this. In fact, a lot of hypotheses tests that we've done are kind of weird to end on. We've ended a lot of, say, two-tailed hypothesis tests that just simply said there's a difference between the parameters. And then we just stop. The problem is over. But in reality of a statistical problem, we would investigate the nature of that difference. That would be the follow-up test. So all we did here is, let's call this is the overall test. And then the follow-up test investigates the chi-square components. We know what the chi-square components add up to. They add up to the test statistic. But what we don't know is what the chi-square components is for every single one of those expected counts. So if you're interested in what the follow-up test looks like, it's going beyond the homework assignment. It's going beyond the exam. I feel like it's kind of rude to just end right over at the overall test without indicating this. So if you decide to discuss this, this is up to you, but it's not required. Let's put here, not required, just as a strong indication that this is a little bit beyond. Here are the chi-squared components. We go to result again. We're selecting the residuals and squaring them. So when you run that, you get these values, all these chi-squared components. And what you want to do is look at the largest ones that you see in this set. The largest components are the reason the whole statistic itself became large. It's the reason we rejected the null hypothesis. And it's telling you the nature of the relationship between region and pollinator. It's telling you why the expected counts, which ones are actually the biggest ones in terms of a reasonable difference. The biggest ones were the moths. The moths were so far off that that looks like the major reason we rejected the null hypothesis. The monarchs, their chi-squared components are pretty minuscule, all below 0.13, for example. Native bees starts to become a little bit bigger, but if we just add that up and do a chi-square test, that's non-significant. That's a small test statistic. So the bees, even though they seem pretty different in terms of absolute difference, in terms of relative difference, they weren't too far from the expected counts. The moths were the problem. If there's no relationship between the regions, Snake River Plain, Boise foothills, and the pollinators whatsoever, the counts we got on moths were actually quite a bit different. So this is the relationship between the two variables, some kind of association with the moths themselves as pollinators. And this goes even further. You can now do confidence intervals for the true proportion of moths pollinating in the Snake River Plain specifically, the milkweed, Same for this other parameter here for Boise foothills. So the follow-up analysis kind of goes on and on. But if this was your statistical problem, you would want to know about that. You wouldn't just end the whole problem saying, yes, there's something going on. You have to go even beyond. But our course is a truly introductory course to statistical methods. So this is where our textbook ends, right here on the overall test. But let's put this back into the problem. Sorry, I got a little bit confused with my windows. If you want to investigate that and say a couple words that the relationship seems to have to do with the moths themselves, that's not a bad thing to add, but not required. And here's the total set of all the syntax that made this problem go through. Well, what we'll do in these notes is, we can't end on just one example. We've got to do at least 2 examples for these kinds of problems. So we're going to take another look into these. Let me cite the conditions again. Kind of missed. Let me try another screenshot. And let's take a look into our next level of context. So this is a real and pretty interesting study that was done in 2000. This one is not an experimental design, so we can't make any conclusions along cause and effect lines about this, even though it might be tempting. And it looks like it has something to do about anger and incidence of CHD, defined as coronary heart disease. So here's how the study went. In year 2000, researchers published findings from the Arteriosclerosis Risk in Communities study. There's an acronym, but I don't think we use it again, so that was probably should have deleted it, which examined how chronic psychological stress impacts cardiovascular health over time. So unlike example 1, this is real data now, making it more exciting for example 2. To measure stress, researchers evaluated the subjects using the Spielberger Trait Anger Scale. So now psychology is involved with this one. This test specifically measures trait anger. We're going to think of trait anger as being your baseline anger level, a baseline personality characteristic indicating how prone a person is to sudden frustration and anger, presumably. So there's trait anger. How naturally prone are you to blowing your top? I guess is a simple way to say it. Then there's also state anger, which is a temporary emotional reaction to a specific event, like I got in a car accident or I just lost my keys. For me, this seems to have to do with cars for some reason. So we're trying not to think about state anger as being part of this because it's temporary. But trait anger is the major thing that they were looking for. Your baseline anger level, that might have more to do with actual cardiovascular risk. So they were really careful in the study to know what they were measuring specifically. So when it says low anger, moderate anger, high anger, we don't mean someone had a bad day. We mean baseline anger. This is a personality characteristic of the person through a bona fide psychological test, which has its own issues, right? These tests aren't perfect. So we hope the sample size is large enough to give us meaningful results. And here's the sample. The data below represents a random sample of 8,474 subjects. So there's our sample size N, who all had normal blood pressure at the start. So they didn't come in with coronary heart issues whatsoever. By excluding individuals with pre-existing high blood pressure, a known primary cause of heart attacks, the researchers were able to isolate trait anger as a variable. So they're all just ordinary people, no issues with blood pressure. The researchers then tracked these individuals for 4 years. So this is an observational study to see if they developed coronary heart disease, CHD, which includes heart attacks and the need for medical treatment for heart disease. So maybe even angina, and they had to be put on a nitroglycerin treatment, anything along those lines. So the observed counts are provided in the two-way table below. So this was a pretty influential study. There's 2 variables here. After 4 years, and everyone came in with a clean bill of health in this study, some of them had coronary heart disease. 53 with low trait anger, 110 with moderate trait anger, and 27 with high anger. And again, the sample size is huge. Plenty of them stayed with no coronary heart disease at the end of the 4 years. 3,057 had low trait anger. 4,621 have moderate trait anger. 606 of them have high trait anger, the kind of people who have like kind of a bulging vein in the forehead type of people. So what can we learn from that? Really hard just looking at this data. First of all, the counts for the categorical variables, way off, right? And there's nothing you can do about that. There's not two independent simple random samples whatsoever this time. This is one random sample measured on two categorical variables, and this is just how the outcomes fell. Any questions or comments at all, folks, about the context so far? Okay, really it's pretty much the same style of a question from example one. This one is asking us to just do a complete analysis instead, but we're gonna hit all of the same parts. Except for this part, this is pretty much the thing that we didn't do in the last example. State the practical question in your own terms that requires statistical inference. You know, there's no question mark here, so that's something we have to infer. I don't see anything we could even directly cite for the practical question. I think once you read the context once and maybe you do it again, a question probably comes into mind. And the natural question is, does anger influence the incidence of coronary heart disease? So that would be a natural question. Again, you could rephrase this in a lot of different ways. It's kind of up to you how you'd like to verbalize that. Whatever you decide to leave here, make sure it makes sense with the hypotheses you set up and the overall conclusion you're going to give at the very end. Make sure that they're compatible. With that down, we're pretty much running through the motions of analyzing this new set of data. For chi-squared, two-way tables, there are two categorical variables, and our first job is to define them. After we define those, we'll know what the null alternative hypotheses are going to be. So here's how it goes. Again, going this way, in this column, outcome after 4 years, that could be one categorical variable. You could give it a lot of different names. Usually it's short. You usually wouldn't say outcome after 4 years. Your name could just be outcome, or it could be coronary heart disease, or the abbreviation CHD. So kind of a hard choice on this one, actually. You know, I'm going to make this variable be a little bit longer just for the sake of descriptiveness. Let's say one variable is, I just want to say exactly coronary heart disease. That's going to be the name of my one variable. Coronary heart disease. We want to describe the variable, so we should say it's categorical. If your variable is categorical, it has to have outcomes. And I'll use the abbreviation to describe the outcomes. CHD versus no CHD. CHD for coronary heart disease after 4 years specifically, as the table's indicating. And then no CHD. So those are the outcomes. And then for other variable, you could call this anger. But you know, they're really careful about one element of the study, that there's kinds of anger, really, according to the psychologists. And they don't care at all about state anger, temporary frustration. It could be severe frustration. It could be true anger, something really bad happened. But we didn't mean a baseline personality anger level. We want to discuss specifically trait anger. So I think that's a good word to include for this variable, just to remind us when we get to our conclusion, that's what this is really all about. So let's say trait anger, or maybe let's keep this the same, another variable, is trait anger. Let's capitalize that, which is typical for defining a variable. Trait anger, categorical, outcomes are low anger, moderate anger, and high anger. So that's our setup so far. So what are we testing? We want to know, is there any relationship at all between these variables? But that's the alternative hypothesis. What we're really going to test is, in full, a null, there is no relationship between, it's the variable specifically, so I'll say coronary heart disease, and trait anger. So that's our null. We're going to test that against the other possibility that there is some kind of relationship. We might have something in mind that the relationship would be, if you're at moderate or high anger, higher incidence of coronary heart disease. But we have to go by the actual data that was given us, that was produced by the researchers rather, and see if it really is significant. So here's this. We might find that there's some other relationship we didn't even think about that could occur in these data. So we're looking for any relationship whatsoever. So we say there is some relationship between coronary heart disease and trait anger. So those are our null and alternative hypotheses. Now let's say here one last statement. Test at alpha equals 0.05. Well, it has all the hallmarks of a statistical question. There's usually a lot of writing before we even get into anything numeric, but we're just about there to start importing the data, cranking out some statistics. Any last questions or thoughts at all, folks, with our hypotheses? Okay, well, for the condition checking coming up next, notice how, sorry for the random scrolling, notice how this problem is fundamentally different on how they got the data. There is one random sample altogether this time. There aren't two independent populations. These subjects were all matched to be as similar as possible with respect to these kinds of traits. However, there are in fact two categorical variables, and so this is also allowed for the chi-square test of two-way tables. So we are in this situation. We have a single simple random sample with each individual classified according to two categorical variables, which is exactly what they did. Here, it just said it was a random sample. It didn't mention the sampling design specifically, but that's good indication we're on the right track. Randomization did occur. So I'll say here to start on condition 1, the sample is random from a single population where two categorical variables was used. So this means this condition is met. that we're wondering now is, if we assume that there's independence between coronary heart disease and Trey-Enger, assuming that the null hypothesis is true, no relationship, will our counts be large enough coming from this table? Sometimes it's a bit of a concern if you see something at 27. It's just going to depend on the data itself using independence. So here's where we're going to start pulling in the data, check both conditions 2 and 3 simultaneously. So I'll put here's the check on conditions 2 and 3 down below. But really, it's just now a matter of importing the new data. If our syntax worked well from us once, it'll work really well again. We can just reuse this. We need different row names, different column names, and definitely different data. But this structure will do the job for any chi-square analysis two-way tables. So first, let's put in the correct data, 53, 110, 27. Go down a row. Next, it's 3057. Going to line up the commas just to make sure it's easy to double check we have the right information. On this value here, 4621. And finally, 606. Next thing to do is double check this a couple times, make sure everything comes out just right. It's easy to transpose a digit and put, say, 3075 instead of 57. You never know how that might influence things. Next thing I need is just different row names. I want, in place of Snake River Plain, just CHD, coronary heart disease. In place of Boise Foothills, let's bring this all the way back. No CHD, so no coronary heart disease. And this is not too bad. We're just going to change out the pollinators for amounts of anger. Low anger, moderate anger, finally, high anger. After that, we've got everything we need. So double check. Let's run this whole thing here. The table format looks about right, but this is the residuals. So we want to first pull down the expected counts. This table right here is what we're checking against. And looks like all categories are greater than 5. So once again, our sample size, again, it was quite a large sample this time. It, even at 8,474 subjects, came in kind of low right there. So it's kind of surprising how easy the conditions can be to fail. So let's pull this whole table in. These are the expected counts. We have to pass both these conditions here in parts 2, parts 3. But if our minimum is already greater than or equal to 5, we can just say all expected counts are greater than or equal to 5. And so the sample size is large enough. So overall, our conditions are now met for this procedure. Let's say that overall, the conditions are met. That means we're just about done. All we need are just a couple more things. We need a test statistic and a p-value. In a complete analysis, when it says carry out the necessary computations, those are the only things we're really ever going after. And we mentioned that pretty much on every complete analysis we've done as a hypothesis test. The test statistic is chi-square. We cite our output here. That's where the Pearson chi-square test is. And it came out to 16.077. But we wrote it in last time, which is always completely fine to do. Let's do a slightly different kind of analysis. I want you to convey that if you're doing this as a homework question or a final exam question, it's okay to just pull in the table. This has every element we need. It has the test statistics stated. It has the p-value. So I'm always going to leave that up to you. You can type it out. You can handwrite it. You can make a screenshot like this. And it gives us pretty much all the necessary computations. And when we see our p-value, it's another pretty small one. This one is less than 0.05, our significance level for this procedure, but didn't make a difference. They're both small p-values. So we will reject H naught once again on this problem, which means we'll say there really is some relationship between having trait anger and coronary heart disease. We'll finalize our overall test. I don't want to rush through it in 4 minutes. This might be a good problem to come back to on Wednesday before we look into how does ANOVA go. In a certain sense, the ANOVA is going to look pretty similar to chapter 21. It's an overall test, just like we're doing here in chapter 22. So maybe last thought, if you're really curious about this, why did we reject the null hypothesis? The largest chi-square component is in coronary heart disease with high anger at 11. The expected count was 27. Excuse me, the actual count is 27. But if the null hypothesis is true, we were expecting only 14 people in that cell. That was nearly double. And so that one cell right here, that alone, is what made our test statistic significant. This one was the next runner up, so that might be statistically significant as well. So that'd be another element of the data to look into. But again, kind of an exciting problem, sort of confirms what we're expecting, that there was an unusually higher count of people with coronary heart disease having high anger, meaning we do have evidence of a particular relationship between those two variables. Well, I think this is, again, a good stopping point for us. I don't want to take up too much time. We're going to finalize the conclusion here and then take a look into our final procedure on ANOVA on our next class on Wednesday. We'll finish up ANOVA when we come back on our Monday's class on the 27th, and we're not going to take too much time in that section because we're wrapping up the course next week. After we finish up our discussion on a couple examples in ANOVA, we're going to convert over to reviewing for the final exam. We'll continue our review on the 29th and then release the final exam on Canvas at the end of that class there. Well, any last questions or thoughts at all, folks, before we call it a night? Okay, well, have a great afternoon, folks. If you know anyone that has a high trait level of anger, you can show them this study. And again, it's a pretty interesting one, easy one to look up. But have a great afternoon.